That's multitasking. So I was going to talk about sea ice because we do sea ice as well, but then I gather Leif Tudal Pedersen taught you about sea ice, so I'm not going to do that. So the mass balance talk will be tomorrow. This is a presentation which shows some really pretty pictures. It's a bit of history about Earth observation of the cryosphere. Hope you're going to stay awake for it. It's not very complicated. It's not very detailed in terms of the scientific techniques, but it's a whirlwind tour through lots of the different things that you can use to study ice, which is a beautiful part of the planet. Earth is a very unique planet. As you know, it has water in liquid, solid, and gaseous phases at any time of the year, and that makes ice in particular a very useful parameter to monitor changes in Earth's environment or climate. So Earth's environment and its climate and changes in those two things are not the same. And satellites can see things, but it's our job to interpret them and actually to improve the way that we see things. So this is two images of Earth from space. On the left-hand side, it's a computer-generated image, which shows everything up in the North Pole very clearly. You can see the land, the sea ice, and the land ice, and the oceans. And on the right-hand side, that's what it really looks like. 40 to 50 to 60% of the time it's covered in clouds, and they're the same color as ice, and that's a problem if you're looking at the cryosphere. And so we like to use more sophisticated tools to study the cryosphere than just optical imagery, but they are beautiful, and this talk will be peppered through lots and lots of photographs of ice. I'll try and whiz through it all because I think I had 60 slides last time and several videos. I'll talk about Earth observations, some really nice things from early days, then optical passive microwave SAR, interferometric SAR, altimetry, gravimetry, and future missions. Basically what these things can show you about the cryosphere. I'm here for the rest of the day and tomorrow. Ask me technical questions if you can, particularly those of you that are interested in the cryosphere and the satellite techniques in more detail, because this will not be detailed. So this is the first rocket that was sent into space 1944, a very long time ago, and it was just a test really to see whether you could aim rockets at people in other places of the planet, but shoot it straight upwards in the first instance, turn it upwards, and it can be a useful scientific tool. This is the first image from a rocket in space, and this is where Earth observation started in the 1940s, when you could see the clouds, and actually people, particularly us in Britain, but other places of the world as well, very interested in the weather. We like to look at the weather, and so Earth observation started out as weather, meteorological satellites, looking at cloud patterns, knowing what was about to hit us or in a while was going to hit us, and so predicting the weather has come on leaps and bounds. In fact, 50 years ago, you wouldn't be able to predict the weather anything more than an hour or two in advance, and now you can do it 2 or 3 days in advance with confidence. This is how telemetry used to work, actually. You might have seen this in your GCSE, in your school days, classes. Jettisoning film canisters from space and caught by aircraft. We don't do this anymore, but this is actually how people tried to collect some samples from space as well. This is actually the first weather satellite image from space, 1960s. This is a satellite that was specifically designed to orbit around Earth, TIROS, and collect measurements from space over time. And this is the first picture of Earth from space, complete picture, really, really beautiful picture. This is a fantastic, iconic image. If it weren't for all of these experiments, almost 70, 80 years ago today, we wouldn't have the space agency that you're sitting in today, and we wouldn't have the measurements that you guys are perhaps working on and hoping to work on in the next 10 or 20 years' time. So it's the exploration that drives scientific knowledge, in fact, and that's something that you have to keep within you, the idea that you want to push the boundaries and are not satisfied with what we have today, because this space agency wouldn't exist if it only had 1 or 2 or 3 year projects ahead of it. It needs 10, 20, 30-year projects to look forward to persuade the governments to invest several billion euros per year. And you guys will be part of the space agency in the future. So Landsat was a satellite taking photographs from space. I've already told you that photographs from space are not particularly good for ice, unless it's cloud-free, and then they look pretty beautiful. 1972, that's when I was born, actually, a long time ago, 46 years ago. So taking measurements from space has been done, photographs from space have been done for a very long time. This is the first Landsat picture of Dallas, Texas. There's no ice there. There was no ice there in the 1970s, and there's none anymore. But there is ice in other places on Earth, which you might not expect. This is Africa. This is a picture taken, well, it's an oblique image photograph generated from a Landsat picture of Mount Kilimanjaro in the 1990s, taken from Landsat at one time of year, and then 7 years later, looking at the same sort of ice. And in the early days, in the 1990s, we didn't know what climate change was. This is still several decades ago. If you look at the first IPCC reports, most of the planet wasn't changing in 1995, and people just got some inkling that things might be happening. And this was the first sort of analysis of environmental change. But the difference between these two images isn't ice at all, it's snow. And we know this in Europe and other places of the planet. It snows at different times of year, and one day in January, one year, will be covered in snow, and another day it won't. So this isn't climate change at all, this is weather. And it's really important to be able to do better than say the ice has changed in between these two images over a 7-year time period, because if you misinterpret a change that's associated with weather, that's nothing at all to do with long-term environmental change. So a lot of ice is trapped up in the global hydrological cycle. So every year, about 6 millimeters of sea level rise works its way through Antarctica through snowfall. And that's a large signal because the global sea level rise is only about 3 millimeters per year. So it's really important to know about the mass transport, the water transport through Earth's climate system, and understand how to detect the signals that are related to interannual variability and the signals that are related to expected seasonal variability. This is perhaps one of the first pictures of ice that was genuinely changing on Earth over a long time period. It's Prince Gustav Channel at the Antarctic Peninsula. And this is a piece of ice that's floating on the sea surface. It's not sea ice, as we've heard about already. It's an ice shelf, so it's several hundred meters thick, and has been there a long time. And this one is bounded in a channel running between the main Antarctic Peninsula on the left-hand side and an island on the right-hand side. And you can see here that it's intact, but later on it disappeared. And this was the first ice shelf collapsing at the Antarctic Peninsula. Back then, it wasn't seen as a precursor to lots and lots of other ice shelf collapses. We now know that things have happened since then, and other ice shelves have collapsed. So this is Prince Gustav Channel at the very northern tip of the peninsula, disappeared in the early 1990s, but then lots of other ice shelves at the Antarctic Peninsula have collapsed. Why is that important? If you do some actual field experiments and collect some measurements from that location and try to understand the geological evidence, you can say that those ice shelves have been around for 10,000 years. And so the changes that we've seen in the past few decades are unprecedented in that timescale, in this interglacial period. And so it matters. We have other measurements from space. This is the space shuttle, really nice. Always, if you go to Los Angeles, you can see one of these. It's really beautiful, walk underneath it. But they used to fly around in space, and it was a very expensive project, and eventually they tried to find reasons to fly these satellite, the space shuttle around in space other than take people into space. And one of those was to take pictures. This is a nice picture of Greenland, really beautiful. It's an expensive photograph. You've got to do better than that. And this is another picture of a glacier, a Kolka glacier. Again, a very expensive photograph, so you shouldn't really be spending many hundreds of billions of dollars to collect photos from space, particularly when it's cloudy over the top of the ice and you can't see anything. But the shuttle did have other instruments on it, and I'll come back to those later on, the precursors to a lot of the interferometric radars that we're familiar with now. International Space Station, that also can be used for scientific observation as well. So there's an observation window there. There's an open competition each year. If you want to bid to have an experiment on the International Space Station, you can do that. Google it and find out how to do it. The call's open most years. Your chances of getting on there are probably slim, but still, it's still an open call. It doesn't fly north or south of 50 degrees, so there's not much ice there, particularly if you're into polar observations. You can't see any of that. But there are some places on Earth within its latitudinal limit where you can see ice. This is a glacier, Uppsala Glacier, within the ground track of the ISS, and a photograph taken from the ISS's observation window. You can see this. You can do better than this with most optical imagery, but there we go. This is something from the ISS. This glacier has changed. So again, if you read Google or some news story coming out of the ISS, they'll say this glacier was changing, but glaciers advance and retreat as part of their natural cycle. And so again, we can see that this is a change in the ice front, but it's not a signal of climate change. Glaciers do advance and then break off again, and icebergs carve. I'll show you some other icebergs later on carving as well. This is a normal thing to happen. You shouldn't be alarmed when an iceberg carves unless you live somewhere where it's going to crash into you. But what you can do with repeat optical imagery, and I just wanted to flick onto this quickly, is track crevasse patterns more sophisticatedly than just taking 2 photographs. And in fact, that ends up today with a routine capability to map ice motion. So this is a beautiful image of Antarctic ice motion from Landsat 8. It's a higher resolution sensor, lots and lots of scientific data available. Alex Gardner and team at JPL composed maps of ice motion for Antarctica over several calendar years, an amazing achievement from an optical image, which is basically photographs from space. You wouldn't expect normally to be able to track ice motion across the whole continent with just optical photographs, but you can, because there's very, very small changes in shadow properties on the ice sheet all over, not just from crevasses, from sastrugi and other features on the ice, allow you to map features and how they move over time with very, very high precision at rates that are interesting to glaciologists. So you can see the river-like network of ice flow across the continent. We can do that with other techniques as well. Passive microwave, I said I wouldn't talk much about sea ice. This is but I'm going to show it anyway because this is a really beautiful animation of how sea ice is mobile. It's a much, much harder problem to address because it's moving around all the time. It's a moving target. I think other people have told you about that. And if you don't observe the whole of the sea ice pack, you really, really don't know whether or not you're tracking just movement of the ice into a different location or long-term change in the signal. But people have tracked the extent of the ice, at least, and we know very, very well from passive microwave measurements, dating back to the 1970s, that the Arctic sea ice cap has retreated in area. The question of whether it's retreated in volume is a different matter. I was going to talk about that. Hopefully Life's told you about that. Anyway, we've not had a capability to track sea ice thickness in the same way as we have sea ice extent for 30 years, 30, 40 years. We've only been able to do that realistically across the whole of the polar hemisphere for about 5 or 10 years since we've had Cryosat measurements. So we can't say for sure what the long-term trend in volume is from measurements. We have to rely on sparse field measurements or reanalysis of those measurements within physical models. But the passive microwave dataset has also been useful for tracking melt extent as well. So this is a really, really familiar animation of the melt extent on Greenland and how that's changed over the past 30 or 40 years as well. And you should all know, even if you're not glaciologists, that Greenland's melting more today than it was 30 or 40 years ago. And this presents a problem because it puts more ice into the oceans. It presents an interesting conundrum for glaciologists because the water sloshing around on the ice sheet changes the way the ice flows around, and that has a positive feedback effect. But it's also very, very interesting for us as Earth observation scientists because it disturbs the natural scattering horizon on the ice sheet surface, which complicates things, particularly for radar measurements. So the scattering horizon for a typical KU band radar might be 5 or 10 meters below the ice surface. And that's fine if that's stable over time, but as soon as you melt the surface, then it jumps straight up to the actual surface, and so you have a step change in the scattering horizon, which is not a change in the elevation at all. And so we have to address that in our satellite altimeter measurements. So it's really important that we know from other measurements that it's in fact occurring. Synthetic aperture radar, great thing is it can see through clouds. We've already heard about that. So this is a photograph from optical imagery, Landsat on the left-hand side of southern England, and on the right-hand side, a radar image, a false colour image of the same area. You can see straight through the clouds. And that's great because it's cloudy a lot of the time, in particular in polar regions. The first genuine synthetic aperture radar systematic mission was CSAT, but it also was actually the multi-sensor mission as well, first multi-sensor mission in late 1970s. It didn't last very long, but it was a proof of concept of effectively radar altimetry and synthetic aperture radar, two really, really important techniques which are very, very powerful for studying the cryosphere. So this is a nice animation. You can see the full thing if you Google it online, of CSAT being launched in 1978, and it collected the first SAR images from space. What's good about those images is they date back to the 1970s in a way that the ERS measurements that we're familiar with from the European Space Agency don't. And they give us a snapshot of Earth at least a decade or more before the first systematic measurements from the dedicated Earth observation satellites that European Space Agency launched. What can you do with those? Well, this is not no ice in here. This is the Pacific Northwest. On the left-hand side, we've already seen lots of images of these from the Oceans talk, I'm sure. That's an image from CSAT processed in 1978 with the telemetry that was available then and the geocoding that you could get from that. And then a reprocessing of that data set, which has happened. The Alaska SAR facility have done this over the past few years. Today shows you actually that the data are much better quality than they were back then. So go back and look at those measurements from CSAT and GeoSat, in fact, because they do contain real value, even though a blurry image from the 1970s might look useless. In fact, as soon as you improve the satellite orbits, you can focus the SAR images much better and get a clearer picture. And the data were just as good back then as they are today. They might not be as systematically acquired, but they're very, very useful and have been used, in particular, in many glaciological applications. The first effective image of Lake Vostok came from synthetic aperture radar, actually. So this is a nice, beautiful image of Lake Vostok from RadarSat in the 1990s. Really big lake that sits beneath Antarctica, beneath a couple of miles of ice, and it's been there for a long time. People are interested in these for lots of different reasons. They're an opportunity to explore extreme environments. They're an opportunity to have a very clear validation site for your satellite measurements. It's really flat on the surface. And they're also just an adventurous location to visit, and lots of people try to get there because this one in particular is in the middle of the ice sheet. There was some interest a few years ago about the water beneath the ice sheets moving from lake to lake, and whether or not that water could end up in the ocean. Lake Vostok has about a centimetre of sea level potential in it. And so even the very, very largest lakes in Antarctica, if they were to be discharged into the oceans, wouldn't really cause a major upset in terms of sea level rise. But we can do more with SAR imagery than just look at individual snapshots. This is a mosaic, an animation of data over Thwaites Glacier, famous glacier in West Antarctica, losing a lot of ice. You can track the ice motion over time just in the same way you can with optical imagery, and you can see the crevasses advecting downstream. And if you have some very simple cross-correlation routine, you can track those patterns quite effectively nowadays with SAR imagery. But you can do better than that. You can use interferometry, and I'll come back to that in a second. And again, another way to track ice from space is to just take these SAR image mosaics. This is Adrian Luckman's data of the iceberg, very famous iceberg that broke off Antarctica in 2017. Just business as usual, in fact, but created a lot of noise. In fact, it was its first birthday earlier this year, I believe, and that even made the news as well, which is disappointing from a glaciological perspective because it's of no consequence whatsoever. But nevertheless, it just does draw attention to satellites and their power, shall we say. Interferometric SAR first came really about systematically thanks to ERAS-2 being launched at the same time as ERAS-1. So this is a plug for not having satellites launched just as the last one dies. Let's have two satellites in space at the same time and see what you can do with it. And we've got that now with Sentinel-1A and B, and we have it with Sentinel-3A and B. And actually you can do new innovative science having two platforms in space at the same time. What could you do with ERAS-1 and 2 a day apart in space? You could do radar interferometry, and that's a very, very different thing to tracking features in optical or SAR imagery, which are incoherent. This is an interferogram for two SAR scenes taken in the early 1990s, published by Dick Goldstein and others in Science, 1993. And it's an interference pattern of the Rutherford Glacier, Rutherford ice stream, in fact, in Antarctica. And it shows lots of different things. From a glaciological perspective, you can really easily understand what's going on here, but it just looks like an oil slick to most people. Down the center of this here, I'm told to use this mouse. Down the center, maybe I could use both at the same time. Down the center here is the main ice stream flowing down the middle. There's a tributary flowing into it. These fringe patterns are just terrain contours. This is the decorrelated area is the shear margin down the edge of the ice stream where we don't get a coherent pattern into the interferogram. This pattern here is really, really important pattern. That's the vertical motion of the ice stream associated with the tide, because this part of the ice stream is floating, and this part of it is on ground, and this location here is the grounding line, and it's the junction between floating and grounded ice. It's the edge of Antarctica. Lots and lots and lots of different signals glaciological in this one single interferogram, and it really did open up a whole different set of glaciological investigation capability, because we could track the terrain height from space, we could track the speed of the central ice stream from space, we could track ocean tides from space and their effect on the ice shelf, and we could track the grounding line. None of these things could have been done before at all, and it wasn't planned. So the missions were just sent up there, and people investigated whether or not you could perform interferometry. And since then, lots of other things have been done. This is a shuttle interferometric image of Malaspina Glacier. It's a 3D composite with Landsat image laid over in South America, because there was an interferometer on the shuttle as well, and that was effectively mapping the terrain height of the glacier. But if this works, it may not work. Seems it hasn't worked. Poor Eric. This is Eric Reno's animation of ice motion. It might work, over Antarctica, tracked from multiple different satellite missions, Landsat, ERAS-1, RADARSat-1 and 2, and possibly some JRS data in there as well. This is the first systematic mosaic for Antarctica. It was published in around 2011 actually, but the data was collected around 2008 in the International Polar Year. And it was the first systematic map of the ice flow pattern in Antarctica from space. We've had maps from Landsat since then, but that suffers from the inability to track through clouds, as I've already said, and also the inability to work during summer as well, during Antarctic winter, should I say. And in Greenland, in particular, in some parts of Antarctica, the ice speed changes throughout the year seasonally, and so we really do need a capability to map at different times of year as well. We can track ice flow across Greenland systematically now, thanks to the old satellite missions, RADARSat and ERAS-1. This is Twyla-Moon and Ian Jockin's work. All those data are freely available at NSIDC. And also now thanks to Sentinel-1A and B. So this is work from Thomas Nagler at MVO, stacking all of the Sentinel-1A images and B images in Greenland for the past 4 years to track the ice motion interannually. And you can chart the speed of individual glaciers. This is Jakobshavn, brave, fastest glacier on Earth. Very interesting place glaciologically, but also a place you can access and you can visit. So go and fly to Ilulissat, which is down here, and it's a really, really beautiful location. You can actually walk up to the main glacier if you want, if you're adventurous, and see the ice pouring into the ocean 15 kilometers a year. You can see the ice move on an hourly basis there. So it's really easy to track the motion of that glacier. And it's responding to changes in its environment like no other glacier on Earth, in fact. It sees very, very strong seasonal cycles in flow, and those are correlated with the ocean properties in the fjord and also with the atmospheric properties inland, which are driving melting at the surface. A really complicated glaciological problem that we've been able to start to address thanks to satellite measurements. Just to touch back on again the ice sheet grounding line, this is a movie now which illustrates how to track the grounding line from space. This is work from Noel Gormlin and others, Yongwon Park, looking at Pine Island Glacier. Just to take a cutaway through the glacier, you'll see what I mean by the grounding line. That's this location here. I have to do it with two things, try and multitask. It's the junction here between ice and the ocean and the bedrock where the ice starts to float, and this is an ice shelf. It's the glacier extending into the ocean, so it's really thick. In Pine Island Glacier's case, it's about 1 kilometre thick at the grounding line, but it still moves up and down with the tide. And when you map the motion of the glacier, this part inland doesn't move up and down with the tide, but the part that's floating does, and it has a vertical component. Because SAR looks sideways, it sees horizontal and vertical motion. And so the vertical motion is actually more prominent than the horizontal motion because it occurs more rapidly. You get a couple of meters of tide cycle per day, whereas even the fastest glaciers on Earth are only traveling tens of meters per day, but this one is traveling about 5 meters a day. So you can see the vertical motion of the floating ice shelf and the limit of where that occurs, and that allows you to track the grounding line. That's important because in parts of Antarctica, the stability of the grounding line tells us about whether the ice sheet will remain in its current location for decades to come. And in fact, this part of Antarctica, the ice sheet grounding line is retreating. And that's a very famous and familiar story from lots and lots of different studies. We can track the grounding line. Grounding lines tracked with synthetic aperture radar interferometry. It only works in special cases where the images remain coherent, and it worked really, really well when we had tandem data from ERS-1 and 2 in the 1990s, 1995 and 6, and maybe 1999 and 2000. Over fast-flowing glaciers, it's really much harder to do that. So Sentinel-1A and B, they're 6 days apart, but most places in Antarctica can be surveyed with Sentinel-1A and B in terms of their grounding line position, but the fast-flowing ice streams can't. So that remains a challenge for the future, to track the grounding line from fast-flowing ice streams. So we need a satellite in order to do that that can remain coherent, and that means reducing the repeat period that we currently have from 1A and B. So altimetry is what I do. I do most of the other stuff as well, but this is what I've done for the past 20 or so years. Fantastic tool. If you're interested in altimetry, come and talk to me afterwards. I'm very, very happy to talk about it at more length, and I'll say some more about it tomorrow as well. I'll try and give you a bit of an altimetry lecture tomorrow as well, in between the sea level rise lecture. But this is the first elevation model from satellite altimetry. Jay Zwally published it in 1989 of an ice sheet, and it's from CSAT data. And CSAT did fly over the southern half of Greenland and the very northern tip of Antarctica. And so those data, like the SAR imagery from CSAT, are still useful to us today. Jay Zwally invented effectively the technique of tracking elevation changes with satellite altimetry over ice sheets from space. And to do that, he used crossing points of the satellite orbits, because if you do that, where the orbits cross, you can cancel out the signal of elevation associated with mislocation of the two orbits, which is effectively the surface slope on the ice sheet. And so you can allow your orbits to drift around in space by up to 1 kilometer or so and still track the elevation change with precision. So on a typical ice sheet, the slope might be 1%. So if your satellite moves 1 kilometer to the left or right, that will lead you to have an elevation change of about 1 meter, say, or 10 meters, in fact. And that's a problem, because that limits the precision with which you can make elevation changes if you don't know your orbit. So you use orbit crossing points, and you can cancel out the terrain slope effect. And Jay did that quite effectively. The problem that he had was that back then, he didn't have a reference point, and he used the sea surface as a reference point for the elevation change of the ice sheet, and he assumed that the sea surface was doing nothing. But we now know that the sea surface is not doing nothing, it's rising. And so there was a miscalculation in this paper, but it doesn't negate the technique that he presented back then. It just exposed the fact that the ocean was rising. This is the first elevation model of Antarctica from radar altimetry. It's really, really beautiful image from John Bamber and others. Well, Bamber and and Bob Binchadler. And it's a composite of ERS data, primarily from the geodetic phase in 1993, but supplemented with data from the other phases of the mission. And you can see lots and lots of glaciological features on this, actually. It's a really powerful image, and I tend to go back to it, even though it's decades old, and there are better elevation models now. Why not use this one? It was the first one that was published, right? And so the guy should get credit for it. You can see Lake Vostok here. I'm going to try and multitask again there with the arrow. Lake Vostok, a very, very flat area on the ice sheet surface. You can see the ice divides here. This is the very summit of East Greenland around here, and that's several kilometers above sea level. You can see these very flat locations. This is Ross Ice Shelf here, and this is Filchner-Ronne Ice Shelf. This is Larsen Ice Shelf. These are the flat ice shelves. They're still quite thick, but because they're floating on the sea surface, we're only seeing the surface expression. They're just like icebergs in that regard. And you can see, actually, the glaciological setting of West Antarctica. This is West Antarctica over here and East Antarctica. It's much, much smaller, but we have a marine-based ice sheet in this sector. And thanks to airborne measurements of ice thickness, we can calculate the bedrock elevation, and we know that West Antarctica sits below sea level and East Antarctica sits above sea level, and that makes West Antarctica susceptible to environmental change because you can deliver a lot more heat via the oceans to a polar ice sheet than you can the atmosphere. So the average temperature, now, it's very cold in Antarctica. This is not a news flash. The average temperature might be minus 30 or 40 degrees centigrade. So to melt that ice from the air, we need a lot of planetary warming. It's not going to happen anytime soon. But the water's wet, which means it's above freezing. And so you can deliver quite a lot of heat to the ice via the ocean. And in fact, this part of West Antarctica, where there is no substantial ice shelf, the ice from West Antarctica drains either in this direction towards Ross ice shelf, this direction towards Filchner-Ronny, or this direction into the Amazon Sea with no ice shelf barrier. This is the susceptible part of the ice sheet, long suspected to be that, and in fact, satellite measurements reveal that it is. And so this is the first elevation change map for Antarctica. Duncan Wingham and others published that with a rather ugly colour scale, but it's collected from ERS-1 measurements in the early 1990s. About 4 years of measurements. We now know that you shouldn't really rely on 4 years of measurements because we can see meteorological fluctuations over those sort of time periods which complicate the signal. But nevertheless, even in this data set, there was a prominent signal of deflation in West Antarctica, which set the ball rolling for investigating that part of the continent. So even if you're not a glaciologist, if you're not in any way interested in ice, you must know that West Antarctica is melting and causing sea level rise, and it's this part of the continent. And it was discovered from satellite altimetry in the late 1990s. We've got a much clearer picture of what's happening there since then. We have laser altimeters, or we've had laser altimeters in space, built on the heritage of the Mars orbiting laser altimeter, MOLA, which was launched in 1996, a decade before we had a laser altimeter on Earth, but that's the way space exploration goes. This map of elevation of the Mars ice cap, it's not really an ice cap, it's a lead deposit of carbon dioxide, was produced well in advance of the elevation model from IceSat on Earth. There was a paper about Mars in last week's Nature issue. You might have seen that one on space. They discovered apparently a subglacial lake beneath the Mars layer deposits. Encourage you to take a look at that paper because it looks like a pile of rubbish from but the news release really went to town and said it was definitely a subglacial lake. If the evidence for the subglacial lake on Mars, this is me on my podium now, if the evidence for that subglacial lake were presented for an Earth-based subglacial lake, it wouldn't get into the Journal of Glaciology. It was just a brightness image, reflectance at the bottom of the ice cap, but because it's over Mars, it got into Nature. I don't believe that it's a subglacial lake, but there we go. We've had decades of people looking for subglacial lakes in Antarctica, and it wouldn't cut the mustard there. But anyway, the Mars orbiting laser altimeter was the precursor to IceSat. They just didn't design the satellite differently, and its lasers burnt out, the first one, because Earth's atmosphere is different to Mars's. And so it didn't last in the way it was meant to, but IceSat-2 is going up later this year or perhaps in January next year. And that will be the next attempt for a systematic laser altimeter from space. Laser altimetry sees a different thing to radar altimetry. So the laser measurements scatter from the true surface of the ice, whereas radar altimeter waveforms do penetrate into the snowpack. And for some glaciological applications, that's a good thing. For others, it's bad. So what a laser altimeter will see, this is a little digression, it will see the pattern of weather, because on top of the ice sheet, I've already told you, it snows and it goes up and down like this. And it will see the pattern of weather superimposed upon any ice thickness changes that are occurring at the same time. And so that pattern of weather needs to be removed from those measurements in order to understand how the ice is changing. A radar altimeter sees through a lot of that weather. It penetrates to maybe 5 meters depth in Antarctica, and most of Antarctica is a desert. It receives very, very small amounts, millimeters per year of snowfall. So if your altimeter signal penetrates 5 meters, that might be 50 years worth of accumulation that you're seeing through. And so it's a long wavelength filter on how the weather is occurring, and so you won't be susceptible to short period fluctuations in the weather, and you'll see more of the ice. So it's horses of courses, whichever one you're interested in. If you want to see the weather, a laser altimeter is a great tool. If you want to see the ice, I would prefer to use a radar altimeter. In fact, in an ideal situation, you would have both, but as the way things go, ESA's radar altimeters cost about 100 million euros. NASA's laser altimeters cost about 1.2 billion euros. And so there's a difference in price that would probably be unpalatable for the European market, shall we say. So what can you do with a laser altimeter, though? Even the measurements from ICESat were able to show, and this is a fuzzy image, not mine, I apologize, show these subglacial lakes, show them up nicely. So this is Helen Fricker's work around the Antarctic Cycle coast, which feeds into the Ross Ice Shelf. Looking at subglacial lakes is a really poor image. I mean, you've really got to squint to see this one. But the subglacial lakes in Antarctica, turns out they're not dormant, and they're not sitting there, and Lake Vostok hasn't been sealed for 2 million years or whatever it is. The water moves like it does under all glaciers and all glacial catchments, moves around from time to time, and it exchanges between the lakes. And you can see that when you look at the altimetry of the surface, because you get ups and downs in systematic locations. It's not weather, it's the up and down of the ice sheet surface as one lake is draining and the other lake is filling. And the water moves between these lakes from time to time, which means you're not going to be able to drill into one of these lakes and find dinosaurs. It's unlikely, because the water's been flushed between these lakes ever since then. But the best thing to look at the polar ice sheets is Cryosat. And this is really the first operational, shall we say, satellite altimeter mission to study the polar regions. It's operational because it didn't break. Well, at least the second one didn't break. The first one is studying the polar regions, only at the bottom of the Arctic Ocean. The second one has been in orbit since 2010 and flies in the near polar orbit. And so it does survey the Antarctic continent altogether, minus a couple of 100 kilometers at the South Pole, and in particular, importantly, the Arctic sea ice cap. And I'm not going to talk so much about the Arctic sea ice at all, but the Antarctic continent in particular has been very, very much better resolved with Cryosat, thanks to its not just its orbit, but its fine spatial resolution as well. And we now have maps of the continental elevation change with much, much finer detail. So this is a montage of Cryosat measurements over Antarctica. We can produce the very simple elevation model of the continent. You can see there the bedrock elevation. Maybe I'll pause that. So this is what I was talking about before. This is the land beneath the Antarctic continent. Over most of East Antarctica, in fact, all of East Antarctica, really, the land is above sea level. When this animation was generated, whoever generated it didn't compensate the bedrock for if you remove the ice load. If you remove the ice load, the Earth's surface goes back up again. And the bedrock beneath East Antarctica is almost everywhere above sea level. It's an island. But West Antarctica is almost everywhere below sea level. It's formed in an ocean basin. It's interesting to think of how an ice sheet might form in an ocean basin. It has to grow on an island, like this island here, or Thurston Island here, at some point, and then start to spread out into the ice, form an ice into the oceans, form an ice shelf. They might coalesce from different areas, and eventually snow falls on that and depresses it over millions of years, and then it starts to rest on the seabed. That's a very different configuration for two reasons. One is because the ocean is then surrounding that ice sheet, and so you can deliver heat, as I've said. But more importantly, the sediments on the seabed are quite fluid, so it's sand. And so ice will slip around on the seabed much more freely than it would over this mountainous terrain in East Antarctica. And we see that. The glaciers in West Antarctica are much more dynamic than those in East Antarctica, just because of the sand and the silt that rest beneath them. And that's important because if you just tip them slightly out of balance, with a little bit of ocean heat, for example, then they can respond really quickly. So we used to think that Antarctica was a sleeping giant, it's easy, a simple phrase to use, and wouldn't respond to environmental change. And in fact, in the first IPCC assessments, I might repeat this tomorrow, the ice sheet was not expected to lose any ice in the next century. And that's because it didn't have a dynamic component in the models at all. They weren't expected to change the pattern of flow. But you only have to look at it with satellite measurements to realize that that's a fundamental misunderstanding of how the ice sheet can behave. And we see doubling of ice speed over 5 to 10 year time periods in many places in Antarctica and Greenland today. And most of them are in places like West Antarctica, where the ice sheet is grounded below sea level and experiences Very, very different boundary conditions to the ice sheet elsewhere. So it's this part of Antarctica that we're concerned about for future sea level rise. And it turns out it's this part of Antarctica that's melting. So we see the pattern of elevation change here very clearly, growing in West Antarctica. These glaciers have thinned by several hundred meters over the past 20 or 30 years. That's quite a very tall amount of ice to lose from the ground. But you can do more with Cryosat. This is a bit of oceans now. You can map the ocean bathymetry from space by looking at the sea surface height gradients. That's a really nice and interesting tool. Dave Samwell and Walter Smith have done that. You can map Greenland's elevation change in the same sort of detail, or you can map the Arctic Ocean basin as well, the seafloor there. And you can map Arctic sea ice as well, and thickness changes, elevation changes, freeboard changes, and then thickness changes of Arctic sea ice. In Greenland, the pattern of ice elevation changes is a bit different to Antarctica. Very little of the Greenland ice sheet is grounded below sea level, but lots and lots of its glaciers flow into fjords, which terminate in the ocean. And we see, particularly in west central Greenland, lots of glacier thinning because the ocean in that part of the planet has warmed quite a bit over the past couple of decades. But more importantly than that, more prominently than that in Greenland, is the signal of surface melting. So the atmosphere has warmed in Greenland. It's not -40 in Greenland. It's more like +10 or +20 in the middle of summer. And so we get lots of melting there each year. And so every extra degree centigrade of heat in the atmosphere does melt more ice from the continent at the edges. And so Greenland, 2/3 of its ice loss is from surface melting. And we can map with Cryosat the pattern of surface elevation change or freeboard of the sea ice for 7 months a year in the Arctic, 12 months of the year in the Antarctic, because there's no melt ponds in the Antarctica. And we can invert that to get sea ice thickness. The last technique I'll talk about really quickly is gravimetry. I still say it's a new technique, but it's actually been around since 2002 now, so it's definitely not new. GRACE, actually a really remarkable tool. 2 satellites in space, measuring the distance between each other, and as they fly around in orbit, Earth pulls them towards itself or away, and their orbits diverge a little bit, and you can invert that distance change to get the Earth's gravity field from space. Not very, very fine resolution, but actually a really, really precise measurement. And that's useful for lots of geophysical applications. You can build a geoid, and this is what Earth really looks like in an exaggerated sense in terms of its equipotential. And that's what pulls the satellite around, in fact, the 2 satellites around in space, predominantly. But the other thing that pulls them around are time variations in Earth's gravity. And that happens a lot because of, when I started this lecture, I talked about the hydrological cycle. Well, water moves around planet Earth all the time, in the oceans, in the atmosphere, and through the biosphere, and actually the cryosphere as well. The biggest signals you can see here, this is time-varying gravity with no color scale, so I apologize there. But blue and red mean the opposite of each other, I guess. And you can see the time variations really prominently in South America, in Brazil. That's the storage of water and release of water during summer and winter in the Amazon rainforest, I guess, and in other parts of the planet. And that actually adds up to quite a lot of mass. And that has to be accounted for, and by measuring the time variation in the Earth's gravity field, you can deduce the water storage on land, for example. But I'm not interested in land, I'm more interested in the cryosphere. And even on this tropical-centric map, you can see that there are changes in the mass in Greenland up here at the top, and changes in the mass in Antarctica at the bottom. Now, when you look at the planet as a whole, it looks like you can resolve these signals and they're geophysically meaningful. And even at the continent, at the scale of the ice sheets, it's still the case that they are geophysically meaningful. So this is Scott Lütke's time series of GRACE measurements for Antarctica. GRACE is measuring the gravitational attraction over the continent, and that's predominantly, the time variation of that is predominantly due to the change in the ice load. And you can see over the lifetime of GRACE, or the lifetime of useful GRACE measurements, 2004 to 2014, there are problems with the mission either end. You can see a trend in ice mass that's emerging in West Antarctica. The same signal we see in velocity measurements, the same signal that we see in altimeter elevation change measurements, but this is actually now a signal of mass change beneath the satellite, located to a fixed location in time. Of course, the satellites are spinning around. But the difference here is that GRACE is weighing all of the planet's mass, and all of the planet's mass change. This has stopped evolving, but there we go, never mind. You can get the picture just about from here. The spatial resolution of this signal is really, really coarse. So when we had, in the velocity maps, a very, very fine pattern of ice flow for Antarctica, this river-like network of flow. And when you look at ice velocity changes, you see this river-like network of speed up. You can't resolve that in the GRACE measurements at all. You can just see the regional or even continental scale change in mass or gravitational attraction. And that's really at the scale of, I guess, half of West Antarctica. So it's really useful if you want to know the total number, how much ice is being lost. Come back to that in a second, but it's not the most powerful glaciological tool. It doesn't tell us really what's causing that change. And in fact, if we didn't have the other measurements from space, we probably wouldn't overinterpret the GRACE signal on its own without any other information. We'd want to go in there and understand what was causing that red blob to emerge at the scale of 1,000 kilometers or so. It could be an atmospheric signal. It could be a lithosphere signal. So the second problem that GRACE unfortunately has, and I don't want to beat up on GRACE because it's been an incredible tool, is that it's measuring the total mass change on the planet at this particular location. And what happens when an ice sheet unloads is the Earth rebounds a little bit. And every time you take some ice mass off, that gets infilled beneath by mantle. And that has much higher density. And in fact, it turns out that over most of Antarctica, the GRACE signal sees zero net mass change. And the inference that this is losing ice is predominantly down to lithosphere models, which say the lithosphere is gaining mass, rock mass. And so it's an offset to the lithosphere models, which aren't observations. And so the GRACE measurements are really, really powerful to look at global mass transports, ins and outs of mass, but we rely on things like models of mantle mass transport to interpret those as well. And we rely upon other measurements, altimetry and velocity measurements, either from interferometry SAR or from optical data, to locate those measurements and understand them glaciologically. I don't know why that animation didn't evolve fully, but the signal would have become more prominent and ended up with the mass loss of around 1,500 gigatons over the final period. So one last slide about future missions, because these are the ones that nobody's looked at data from yet. Up here is Sentinel-3B. Okay, Sentinel-3A is in space already, but 3B is in, Craig Donlan managed to persuade Copernicus to stick it in a curious orbit and keep it maintained in a curious orbit for the first commissioning phase. And so it's in a near repeat orbit right now. And that's the first time we've had a short tandem repeat orbit. I think it's 30 seconds behind Sentinel-3A at the moment. And it's collecting measurements that are almost contemporaneous but slightly offset. And so there are interesting things you can do with those measurements. And however long we're able to maintain the satellite in that configuration, we'll be able to explore new scientific opportunities with those data. So this commissioning phase of about 3 months, nominally 3 months, will be really interesting for things like sea ice flows. So the sea ice does move around within a 30-second time period, and the ocean currents do move around within a 30-second time period. So there'll be new science emerging from the commissioning phase of Sentinel-3B and 3A. At some point, this GRACE follow-on will be commissioned. It's been launched now into space, and it's the same class of sensor as GRACE. It has a different method of measuring the separation in space. I think it's got a laser as well as a Ka-band radar measurement, so it's in principle more precise in terms of its measurement of the gravity field, the absolute gravity field, but it doesn't get better spatial resolution, unfortunately. To get better spatial resolution, you've got to fly at a lower orbit altitude, and then you'll just crash into the International Space Station, which is not good news, or back to Earth very quickly, which is also not good news. ISAT-2 is going to launch nominally in January. It has been beset by delays, but still, there is an actual ISAT-2 somewhere, and it is no longer, it's now vibration tested, and so it should be able to be launched. That's going to collect lots and lots of data. So that'll be in space next year. You'll get the data about a year later, I think, from the NASA science team. And then in the future, so that's the next generation of satellite altimeter. And in the future, you'll have NISAR, which is a dedicated SAR mission for looking at, well, we'll have a dedicated interferometric acquisition strategy for the polar regions, and that's a joint NASA Indian Space Research Organization mission. So there's actually never been more glaciological missions on the horizon than there are today. And when I first used to give this sort of lecture, I used to say, well, we've had to make do with ocean-going missions to look at the polar ice sheets ever since I was a lad. And that was true. We used to use all those earlier missions were not designed for polar regions. In particular, they didn't fly over the polar regions, so they weren't collecting measurements, or only at the peripheries. And they're not designed to look at surfaces which are steep, like glaciers. But they were adapted, the missions were adapted in many different ways. The products were adapted to give useful information about the polar regions. And that persuaded engineers to design missions specifically for the polar region. So all of these data sets will be available in the future, and so you've got to discover something new with them, right? And that's the problem. Are there any things left to discover? There must be. I personally think that the past 10 or 20 years, and I'll talk about this tomorrow, and I'm sorry, I was lucky to be around during that time period, people have been obsessed with the sea level contribution due to Glacier X, Glacier Y, Ice Sheet X, and Ice Sheet Y. And I think that problem is now solved, and that actually leads us back to glaciology again, because that's really climate science. These satellites will in fact unlock the problems that have been around for 40 or 50 or even 100 years in glaciology that none of the missions, which are good looking at continental scale, are able to help us with. These missions will all help us with those small-scale, fundamental physical problems of Earth sciences, which are actually less eye-catching to the media, I guess, but more about what science is. So hopefully we'll be able to solve most of the scientific problems in the next 10 years or so. Happy to answer any questions.
Okay, there's a question at the back.
Is it working? Just talking about the ISAT and the comparison between ISAT 1 and ISAT 2, what would be the advantages of using photon counting compared to full waveform?
That's a good question, and it's still being asked. The advantages are not clearly scientific; they're engineering, and so part of the reason we have space exploration is to push forward the space industry and the space sector and society at large. And the answer is it's not clear whether full waveforms or photon counting are a better thing to do. So Jay Zwally, the original science PI for ISAT, was not a fan of photon counting, but he was brought around to the idea, I think, because it increased the chances of the mission being built. But it will deliver a lot of data as well, a very, very large data product, which will be a headache for anyone to use. And I suspect that we'll all end up using level 3 or 4 products from the science team, which is a disappointing thing, because that's partly what happened with Grace. It will be high. You mean vertical resolution or spatial resolution? Yeah, but then that's partly due to the 6 beams as well. And so it's designed, the mission is designed to be fine. It's like a swath LiDAR, effectively. It's designed to be like a swath LiDAR and deliver more than just a measurement at the sub-satellite ground track.
Any other questions? Yep.
Thank you. When you were showing the pictures of the INSAR images of the glacier, what sort of vertical height change can you see with INSAR?
So if you're looking at solid Earth, where the signal remains stable over long decadal time periods, you can track rates of 0.1 millimeters per year. But we can't see that over ice, because the only time we can measure vertical signals is over very short time intervals, like 1 day. And what we can measure is a fraction of a wavelength. So the wavelength is 5.6 centimeters typically for C-band SAR. And so we can measure maybe a tenth of a wavelength, so 0.5 centimeters, 5 millimeters. But that's still an easy signal to detect when we're looking at ocean tide changes. So ocean tide changes, the tide fluctuation on an ice shelf, the cycle at the grounding line can be up to 8 meters. Because the water column gets really, really compressed at the grounding line. It's very narrow. That's in extreme locations, but it's definitely of the order meters, and we can usually always see. It's harder to find a differential interferogram of an ice shelf that doesn't show the tidal signal than one that does.
Okay, thank you.
Okay.
Do you think that thermal remote sensing has a role to play in cryosphere kind of observations?
I did have an AVHRR slide and I deleted it, and I don't know whether that answers the question. I mean, it must do, right? One of the problems that we have today, ongoing, so some of the unsolved problems in glaciology are Arctic sea ice during the summer and Antarctic sea ice in general. And both of those are somehow related to the thermal properties of the sea ice pack and the snow that's on top of it. In the Arctic, we get melt ponds across the sea ice, and they cause problems for the radar, interpreting the radar altimeter signal. We have to be able to do better for those 5 months of the year when there's still sea ice presence in the Arctic, but the radar altimeters at the moment, the algorithms are not tracking it. And the way to get around that is to be able to detect the water. So looking at the thermal signal is bound to be of use there. In the Antarctic sea ice, we can. There's no melt ponds, but actually the electromagnetic properties of the snow on top of the sea ice start to become really important, and they're affected by the temperature of the air that's above the snow as well. And so it's going to be important to know something about the brightness temperature of the Antarctic sea ice pack to understand the scattering horizon. Because at the moment, sea ice. I don't want to talk about sea ice, but sea ice. The measurement is a relative measurement, the freeboard, the bit that's popping out above the ocean surface. And so sea ice might be 2 meters in thick on average. The freeboard is 20 centimeters. But in Antarctica, we don't see much more than 3 or 4 centimeters freeboard in a radar measurement. And that's because it's penetrating straight through the snowpack. And so that's why we can't get sea ice thickness in Antarctica. We need to understand what the snowpack properties are. And then the other area is for looking at the melt extent, which is driving most of the mass loss in Greenland. And so I gave the passive microwave brightness temperature map, but I think there's been some work from Thomas Moat looking at active microwave brightness temperatures to map the melt extent from Greenland, and you can do that just the same. So it does work. And in fact, my PhD was on ATSR. So I mean, I started out with radiated transfer models, but don't use them so much in the polar regions.
Okay.
Thank you for the interesting talk. Could you please comment on the albedo effect measurements through? Is it possible through, or how is it being done? Albedo.
Yeah, I know. So over land ice, albedo effects are restricted to curiosities. So looking at the darkening of the Greenland ice sheet, for instance, due to the deposition of carbon on the surface, or the growth of organic matter in different parts of the continent associated with climate warming. But these are at the 1-2% change in the ice sheet albedo level. They're detectable, and so they're interesting scientifically. They're not a major signal of climate change. They're definitely not going to drive a feedback in terms of the ice loss in the next century. But you can detect them from space. You can detect the darkening of the ice, and that tells us something about what's going on the planet. The general albedo effect of the sea ice extent, well, that's relatively easy to track because we can see the waxing and waning of sea ice in almost every satellite measurement that we collect from space. The conundrum there is the difference to what's happening in the northern and southern hemisphere. In the northern hemisphere, we've had a progressive decline in the extent of sea ice, and it's retreated to the area of multi-year ice, effectively, not much larger than that now in the northern hemisphere. But in the southern hemisphere, not much has changed, and so there is a question as to what's driving that imbalance in the North and South Pole.
Thank you.
Okay. If there are no other questions, I just have a very quick question.
Go for it.
So you referred to the recent publication on the MARSIS discovery of water beneath the ice.
Yeah.
So the MARSIS instrument apparently used a very low frequency radar altimeter.
P-band radar.
Right. Okay. But the radar altimeters that are used here are mainly kind of KU band. You know, they're very high frequency.
Yeah. So we detect lakes using ground-based P-band radar and low-frequency radar, or airborne low-frequency radar. And we have the same classes of measurements either at surface or airborne, so they're much finer spatial resolution. And what you find when you look at fine spatial resolution is that that things that you might see at coarse spatial resolution can be misleading, and so a very coarse satellite measurement of a blob of brightness beneath a continental ice sheet could easily be misinterpreted as a lake, for example.
Yeah, because it'd be very coarse resolution if you flew it from space, I guess.
Yeah, it is. I mean, read the paper. I mean, I was unimpressed, but there we go.
Okay. Thank you very much. So now we can go for...